welcome everyone to 3.5. We are finally getting into derivatives from a numerical and graphical viewpoint. So this idea, derivative is another fancy term for slope at a point. And this is, of course, we needed to take a pit stop first here in 3.1 to learn a little bit about limits, but now we're ready to actually apply these things to the big first topic here in calculus. Okay, so let's get to it. This first definition talks about an instantaneous, oops, I guess I need a pen out. Fine. There we go. All right, the instantaneous rate of change. So this is, kind of with relations to the average rate of change. So this is talking about an instantaneous rate of change, or instead of slope, at 2 points, or slope at a secant line, we're going to do slope at a point. Just as I promised. Okay, so this of course relies on a function, f of x, at a very specific point a. And in order to do this, well, again, we can't use our slope function for just 1 point. We're going to use it with 2 points. And the claim is that these points are going to be very, very close together. We're going to take a limit here. The only difference is that there's this h, and this h is going to be going closer and closer to 0. So actually, q is going to be getting very, very close to p. So if I use or abuse this limit notation, q is going to be getting very, very close to p. All right, so this stuff up here is kind of crazy looking. Let's actually bring it all together with a picture. So, okay, picture time. I'm going to go ahead and draw some function here. Let's see, maybe my function looks something like this. Here's f, that's a horrible f. Here we go, f of x. And I'm interested in the slope at this point, or the instantaneous rate of change. And so we've already seen, back when we were visualizing these things, kind of in 3.4, the instantaneous rate of change, or the slope at the point, is going to be this slope right here, the slope that just kind of barely skims at this 1 point right here. But we can't use our slope formula to figure this out. So instead, I'm going to take, well, this is my P point right here. Maybe I'll label this here, P. This is my P point. I'm going to choose another point very, very close to it. So imagine maybe it's over here right now, Q. And so if I drop this down, the claim is these are distance h away. So this is going to be a plus h, for instance. Okay. And h is going to be getting smaller and smaller and smaller. Again, you can think about q getting closer and closer to p. And when you do that, the claim is if you start looking at secant lines, or slopes of secant lines, again, maybe first it's over here, and the slope here is pretty close to this instantaneous rate of change, this slope at this point, p, right? But as q gets closer and closer, let's maybe take this last one here, you can see that the slope between these, the green line and that second red line, it kind of went away here, are very, very close. So the claim is the closer q is to p, that average rate of change is going to approximate the instantaneous rate of change. So the closer h is to 0, the better. Okay, this has another term to it, right? This section is called derivatives. So this, another name for instantaneous rate of change, or another name for slope at a point, is the derivative. So derivative of f of x at a. So the derivative of f of x at a, and is denoted f of a, but then you have this little prime symbol, this little, it's almost like a quotation mark, but just one of them. So it's f prime at a. Right? Or the derivative of f at a. So that's how you denote this instantaneous rate of change, or the slope of the point, or the derivative, right? F prime of a. So, in this section, I guess before I get to this example, let me go over this quick remark here. Just like, really, because this instantaneous rate of change is this limit of average rates of change, the units for the derivative, or the units for the slope of the point, or the units for this instantaneous rate of change are going to be the same as the units for the average rate of change. And so remember, the units for the average rate of change were the units of f divided by the units of x. And this is very important because, again, this class, we want to apply this stuff to real-world problems. And so we need to know what kind of quantity is this giving us, right? So, before we get to that, though, let's try an example. In this section, we're going to be, again, because we're taking a numerical and graphical viewpoint of this and not so much an algebraic viewpoint, we're going to be doing some approximations in this section. Next section, we're going to be using our limit information to really calculate this out as precise as you want. So, we're going to calculate out this average rate of change. Remember, average rate of change is good at approximating the instantaneous rate of change so long as the points are close together. So you can see these points are quite close together, 3 and 3.01. This is an h value of 0.01, right? They're only off by 1/100th. So the claim is this average rate of change will do a pretty good job of approximating the instantaneous rate of change at 3. That's another name, of course, for the derivative of f at 3. Let's do it. The average rate of change formula, we know this back from 3.4. That's going to be f of 3.01 minus f of 3 divided by 3.01 minus 3. So, right, this is the change in our y values divided by our change in the x values, right? So this is going to be essentially a slope formula. So, let's get to it. Now, here's where I need to pull out my calculator. And remember that f is given to us up here. It's a very specific function, 1 minus x squared. So let's go ahead and pull out our calculator here and do some quick calculations. So f of 3.01. So I need to plug in 3.01 everywhere I see an x. So 1 minus 3.01 quantity squared. And from that, I need to subtract away f of 3. So this is going to be f of 3. So everywhere I see an x, I'm going to plug in a 3 minus 3 quantity squared. So that's going to be negative 8. And it's important, right, because you want to make sure you show in your work. So let's go ahead and write some of this stuff down. So negative 8.061 minus negative 8 divided by, and 3.01 minus 3, that's going to be 1/100th here. All right, let's go ahead and continue. Oops, wrong one here. So let's see, when I subtract these two things, again, minus a negative 8, let me do this trick here. I'm going to do answer, oops, not that one, entry. I want to get back to this value here. And I'm going to subtract away negative 8. So that's going to be the same thing as adding 8. So you get this 0.061, the negative sign there. And then I'm going to divide by 0.01. So divide by 0.01. And that's going to give me negative 6.01. Negative 6.01. So already I'm thinking that the instantaneous rate of change is probably negative 6. But to be sure, let's take an even smaller interval, right? So that's part A. Part B, an even smaller interval, something very, very close to 3. Now our h value is off by only 1/1000th, right? And so let's check it out. So f of 3.001 minus f of 3, we actually already know that's 8, divided by 3.001 minus 3. So let's go ahead and use our calculator. 1 minus 3.001 squared. And to that we're going to subtract away negative 8. So that's the same thing as adding 8. So when I add 8 to that, that's going to give me, let's see, negative 0.006001. Let's go ahead and write that down. Negative 0.006001. I don't know why I did that extra decimal point. 0.06001. Divide by 3.001 minus 3, so that's going to be 0.001 left over. So I need to divide by, I don't know why I like this thing so much. Divide by 1/1000th, 0.001. And so this is negative 6.001 equals negative 6.001. So you can see that this is even closer to negative 6. Up here we are off by 1/100th. Now we're only off by 1/1000th. I definitely think that this f prime of 3 is going to be negative 6. F prime of 3 is going to be equal to negative 6. So this is how we can use an average rate of change over a very small interval, right? It's 2 points very, very close to each other. In this case, they were only off by 1/100th and 1/1000th, right? Very, very close to each other to approximate what is this instantaneous rate of change, or the derivative, or the slope of the point, right? That's how we actually use these formulas. All right. Let's try this, but you can see another example here where I don't have an equation given to me. I just have a graph. So you need to be able to visualize and remember what these things actually mean. So the first couple here that I have, f of 1 and f of 2, this doesn't even talk about the derivative. This is just because when we start juggling this notation, sometimes it gets confusing. So I wanted to remind us really quick. F of 1 means the height of the function at x equals 1. So this height here of our function at x equals 1 appears to be halfway between 0 and 1, so I'm going to say 0.5. F of 2. So this is the height of the function when x is equal to 2. Okay, this seems halfway between 1 and 2, so that's going to be 1.5 based on the graph there. And now here's where really, oops, that equal sign almost looked like a negative. All right, this is where we really get into the calculus, right? F prime of 3, what is the derivative of f around 3? This is asking what is the instantaneous rate of change, or what is the slope of the point of our function at 3? So if I zoom in here, and again, I'm interested in what is the slope, or what is the instantaneous rate of change for this point. And so if I was to try to draw this slope that just barely skims this point, it looks like the line has slope 0, right? It seems to be a completely horizontal line. It's not increasing or decreasing or anything. It seems to be completely flat. So the slope of this line would be 0, because again, if we think about slope as rise over run, well, there's no rise, right? No matter what the run is, maybe 1 or 2 or 3 or whatever, but there's no rise. So the slope is going to be 0 divided by 1 is 0. Oops, that's a horrible 0. There we go. So therefore, I think the derivative there should be 0. Now let's try to approximate f prime at 4. Again, using the graph, we're going to approximate the derivative at 4. So I want to know what is the slope of the line here. So again, I'm going to try to skim this graph, try to get the slope at the point. So I'm going to just try to barely skim this, just touching this, and I want to approximate the slope of this line. Well, it kind of helps to continue on a little bit to approximate this. So I'm going to get focused in on, I think it hits here, and then pretty close to down here. So the run of 1 and a rise of -2. So I would say that this slope right here is pretty close to -2 over 1, or that's going to be -2. Again, with a graph, really all you can do is approximate. And so there's some forgiveness, right? If you had said -0.8 or something like this, but certainly the slope at this point is negative, right? So the function's decreasing here. So if you wrote 0 or anything positive, that would be wrong. And then based on your work, right, again, these things can be off by a little bit. So that's a good approximation. Okay, so this kind of gets into another point here, right? So this line that I keep on drawing to approximate the derivative, or to approximate the instantaneous rate of change, or to approximate the slope of the point, this has a name. So I want to tell you a little bit about this line that I keep on drawing here. So the line through the point, a f of a, right, so the y value is whatever the function's height is, that's f of a, with a slope of f prime of a, so the derivative, or the instantaneous rate of change, or the slope at the point, right, if it exists, of course, is called the tangent line. So that's that little line that I keep on drawing here, the tangent line. So notice it has the slope, which is the derivative. This has an equation, right? We can actually write this down. So the equation for the tangent line of f of x at a is given by y minus f of a, so whatever this value is equal to f prime at a, so the derivative of f at a, times x minus a. And so if you remember your good old point slope formula, this of course comes exactly from that. So if you wanted to actually prove this, you would use the point slope formula, which says that y minus y naught is equal to m times x minus x naught. Kind of separated these things a little bit. Maybe I'll move this m over a little bit. So this is an equation for a line with slope m that goes through the point x naught, y naught. So in this case, our point that we want to go through is a f of a, and we want it to have slope f prime of a. So that's where this thing comes from. But that gives us the equation of this tangent line. And you'll see this. This will come up a few times in your homework, may even come up in a quiz or an exam. So I want you to know how to get an equation for this line. Okay, like I promised, right, we're actually going to be applying these things. This has some real-world analogies to it. We would actually want to know instantaneous rate of change. So here's an example of how this can be used. Suppose I throw a ball upward, has an initial speed of 30 feet per second. You may know from your favorite physics class that then the height is given by some formula like this. 4 plus 30t minus 16t squared. And this is the height, so it's going to be units of feet for a specific time t after I let go. So I want to find a ball's average velocity. Average velocity, you should be thinking about the average rate of change. On average, how much is the height changing? So if I want to know the ball's average velocity, again, I want to use the average rate of change formula. So I'm going to do s of 2 minus s of 1. Notice that these have units feet, and divide by 2 minus 1. Remember, these are units of time, right? Seconds after I let go. So 2 seconds minus 1 second. So these have units seconds. So you can see the units work out. This is going to be feet per second. All right, so if I plug in 2 everywhere I see a t, right? S of 2. Let's go ahead and do that. On. All right. 4 plus 30 times 2 minus 16 times 2 squared. That'll be 4. Oh, that happens to be 0. How nice. All right, how about 4 plus 30 times 1 minus 16 times 1 squared? That's going to be 18. So I have 0 minus 18 divided by 2 minus 1, that'll be 1. Again, my units are feet per second. So that's going to be negative 18 feet per second. So on average, the ball is going negative 18 feet per second on this interval from 1 to 2. So that's really information that we could have used in 3.4, right? This is a question that definitely belongs in 3.4. How about part B? The ball's instantaneous velocity, 1 second after I let go. So what is the ball's instantaneous velocity? Well, in order to approximate this, we're going to still use the average rate of change formula, but we're going to do it over a very, very small interval. So I'm going to do maybe from 1.001 to 1. 1.001 to 1. And this is going to approximate the ball's instantaneous velocity 1 second after I let go. All right. So let's go ahead back here. And let's see. I'm going to do this little bit of a trick here. I'm going to use the store trick, right? So I'm going to use the variable a, and I'm going to store this as 1.001. And sorry, I used that the other way around. I need to do 1.001, and I'm going to store this as a. So this is very nice. Now whenever I type a, it knows it's 1.001. This is a cool calculator trick here. Watch what I can do with this. 4 plus 30a minus 16 times a squared. You know what? I forgot the times right here. Insert a time symbol. So there we go. That's very nice. And now I can subtract away. We already know s of 1 is equal to 18. Right? So s of 1 is equal to 18. Let's go ahead and subtract that away. Subtract away. Oops. Delete. Oops. Man, I'm just all over the place right now. Delete. So I'm going to do minus 18. Oh, it didn't bring up my answer. Oh no. Oh, this is going downhill fast. This is where I wish I could do some editing. 30 times a minus 16 times a squared. Here's our answer again. Now I'm going to subtract away 18. There we go. Let me go ahead and write some of this down. So this is 17.99 and change minus 18. That change is really going to make a difference though, so that's why I'm keeping it exact on my calculator, because again, it will really make a difference here. So 7.997984. So I subtracted away 18, and now I need to divide by 1/1000. So divide by 0.001. So negative 2.016. Negative 2.016. And again, my units are going to be feet per second, right? And that's why it's going to be giving us velocity. Feet per second are going to be velocity. All right, so that's where I get the negative 2.016. I would approximate, the instantaneous velocity is probably going to be negative 2. Negative 2 feet per second. So use B to determine if 1 second after I let the ball, let go, is the ball on its way up or down. So if it has a negative velocity, I would say that it's on its way down, right? Because it's going to be going, down some feet per second. It's not going to be on the rise, right? Because I guess imagine a ball really quick. If I threw a ball up, it's going to go up for a while and then it's going to come down. So I think because it has a negative velocity, it's going to be on its way down, something like this. So I'm going to say the ball is on its way down at t equals 1. I'll include the units. T equals 1 second, because the instantaneous velocity is negative. So this is a good way to justify our answer, right? That's why I chose it's on its way down. All right, that is the end of 3.5. I will see you guys next time when we actually tackle calculating out exactly what the derivative is using our limits. All right, I'll see you then.